Okay, if I don't hear otherwise, I'm going to assume everyone can hear and see me okay. But like Christian said, I'm a graduate student who works in CMS collaboration here. And today I'll be talking to you about our group's work on our search for supersymmetry, specifically in compressed electroweak scenarios. And what I've been doing on this analysis is implementing a novel fake lepton estimation method. So to just give you guys a quick overview of where this talk is headed, I'll first give a brief introduction into the standard model, which is the overarching theory of particle physics. I'll give you guys a little bit of insight into why it is not exactly complete and how a theory called supersymmetry could potentially answer some of the questions that arise in the standard model. From there, I'll give a brief introduction to the Large Hadron Collider and specifically the CMS detector, which is the detector that our group at KU works on here. And then I'll talk about how particle physicists look for evidences of supersymmetry in the data that they receive from the Large Hadron Collider. And specifically, the method that we're implementing in this analysis is something called recursive jigsaw reconstruction, which was developed by Professor Rogan. I'll then talk a little bit more about what compressed scenarios mean, and then I'll introduce the fake lepton background and what is usually done to account for that in supersymmetry searches and how our method differs and what we hope to learn from it. And then I'll wrap things up with some preliminary results from this analysis. But to begin with, we have, of course, the standard model. I'm sure many of you have seen graphics like this or similar in other particle physics talks. And the reason that particle physicists always begin with the standard model or include it at some point during their talk is because it's fundamental not only to the work that we do, but to the universe that we live in and how we understand it. And so I like to think of the standard model as kind of the building blocks of our universe. And there's a lot of things I could say about it, but for the sake of brevity, I'll give you guys just a quick whistle-stop tour of what particles make up the standard model. To begin with, if you can see my cursor up here in the upper left-hand side, we have these four particles, which are called quarks. And the quarks that you guys might most be familiar with are the up quark and the down quark. These quarks can combine to create protons and neutrons, and as we know, protons, neutrons, and another elementary particle called electrons make up atoms, atoms make up molecules, and molecules make up everything we see, touch, and interact with on a daily basis. However, electrons are not quarks. They're a different kind of elementary particle called leptons, and so the other leptons are the mu, the tau particles, and then each of these three leptons have their own neutrino counterparts. And we can combine the family of quarks with the family of leptons to create this big family of 12 particles called fermions. Fermions all have half integer spin in comparison to bosons, which are these four particles over here. Bosons all have integer spin, and bosons are the force carriers or force mediators of the universe. So we have the gluon, which mediates the strong force, the photon, which mediates the electromagnetic force, also known as light, then the W and Z bosons, which mediate the weak force. And we have this other boson here, which is still a boson, but it's a little bit different. It's separated from the other four. This is the Higgs boson, which you might have heard of. And this was such a groundbreaking discovery, discovered both by the ATLAS and CMS detectors in 2012, because this is the particle that up until then was only theorized to give everything in the universe mass. And once its discovery was confirmed, the theorists behind the Higgs boson actually received the Nobel Prize in 2013. And the standard model is a wonderful tool we can use to accurately predict many things about our universe, but there are still some pretty open questions in this theory. For one, as you can see just on this slide alone, the standard model only takes into account three of the four fundamental forces of the universe. Gravity, or its theoretical quantization, the graviton, is conspicuously left out. And the exclusion of gravity from the model of the universe is not the only open question that this theory has. For example, the standard model doesn't account for dark matter. It also doesn't account for dark energy. We also don't know why there is more matter than antimatter in the universe. This is something the standard model doesn't answer. The structure of the standard model is also something that's currently under study. So we have these three generations or families, and we don't know why there's specifically three, why are there not two, why is there not four? So that's something, another question that the standard model poses. And then a more technical not necessarily a problem with the standard model, but it's kind of, again, an open question is this issue of the mass hierarchy, which is due to these virtual particles that pop in and out of existence in the vacuum, giving the quadratic Higgs mass such great contributions that it diverges. is not accounted for in the standard model. We don't know why the Higgs mass is stabilized the way it is. And so one theory that could potentially address these questions is something called supersymmetry. And it sounds pretty science fiction-y, but the underlying idea of supersymmetry is actually fairly intuitive. So the standard model intrinsically has several symmetries going on, and the theory of supersymmetry just takes that one step further and says, hey, what if every particle in the standard model had a friend or had a super partner? And this is what these larger, fuzzier particles represent with the little tilde on top of them. So for all of the fermions in the standard model, you would get a super partner that has an integer spin whose name starts with an S. So for the half integer spin muon, you would get an integer spin smuon in supersymmetry. Similarly, for bosons, which in the standard model have integer spin, you would get half integer spin superpartners. And the naming convention goes that your superpartners have an eno at the end of their names. So for a standard model gluon, you'd have a supersymmetric gluino. And the reason that supersymmetry is such an appealing theory is because it addresses some of the discrepancies in the standard model in this natural and kind of almost intuitive way. To get a little technical, the additional parameters introduced with the theory of supersymmetry actually cancel the standard model quadratically divergent terms, addressing this hierarchy problem. Supersymmetry also provides a candidate for dark matter in the form of the LSP, or lightest supersymmetric particle, seen in these Feynman diagrams. Move my zoom window around here, here, and here. This chi01 tilde particle is the lightest supersymmetric particle. It is stable. It is not interacting with matter, which makes it a good candidate for dark matter. Supersymmetry also opens the door for force unification. And in this analysis specifically, we want to look for supersymmetry at the electroweak scale, because these superpartners, or these superparticles, or sparticles for short, should be able to be produced at the current LHC center of mass energy. Oops. And so the current status of supersymmetry searches can be summed up in this table here. And I know there's a lot going on, but what you just need to know is, according to this mass scale down here on the x-axis, the highest masses of supersymmetric particles that we have probed so far with the LHC only extend to about 2 tera electron volts. And we've gotten up to this mass and obviously haven't seen any evidence of SUSY, or convincing evidences of SUSY yet, otherwise you would have heard about it. One way we could look for supersymmetry is in this compressed regime. This is some place where supersymmetry might be hiding, and I'll talk a little bit more later about what compressed supersymmetry is and why it's a little bit difficult to observe with our detector. So the way we look for supersymmetry just in general is with technology like the Large Hadron Collider, or the LHC for short. And the LHC is a 27-kilometer circumference ring straddling the Swiss-French border, located in Geneva, Switzerland. It collides protons and other particles at nearly the speed of light. And the way we're able to see what comes out of these collisions is with these detectors or experiments strategically set up around the ring at interaction points to take snapshots of these particles. And the 4 main detectors at the Large Hadron Collider are the LHCb experiment up here, the ATLAS experiment, the ALICE experiment, and then all the way across the ring we have the CMS experiment, which is the detector that we at KU work on. So much like onions or ogres, detectors have layers. And the layers of the Compact Muon Solenoid detector are as follows. So the innermost layer down here is called the tracking layer. So when particles collide in the middle and then, a bunch of stuff shoots out, this is where that stuff, or those particles, begin to leave their tracks. Surrounding the tracking layer, we have 2 types of calorimeters. So we have first the electromagnetic calorimeter and then the hadronic calorimeter surrounding that. And what we can do is combine the information we get from the tracking layer and these calorimeter layers to identify or reconstruct the particles that come out of these collisions. And so when we get interesting things that happen in these collisions, we call these events. These could be potential particle candidates, just as one example. And then surrounding the calorimeter, we have the solenoid layer, which is where the Compact Muon Solenoid gets its name. And then surrounding the solenoid, we get the muon part of the Compact Muon Solenoid, which are these muon chambers. And now muons only live for a fraction of a second, but they are not easily stopped by matter. And so while most particles leave their energy deposits and are stopped in the calorimeter layers, muons actually keep going. And so we want to get as much information as we can from the muons, which is why we have these great big muon chambers all the way at the edges of the detector. And so The way we look for evidences of supersymmetry from the data that we receive from the Large Hadron Collider and the Compact Muon Solenoid detector is that we want to separate these events into signal events, which are interesting and point to potentially new physics, and background events, which are old physics. And just as an example of what some new physics could look like, I have these Feynman diagrams up here. And then, of course, background or old physics is everything included in the standard model. Specifically, in this analysis, we want to look for events that have leptons in their final states. So leptons, as a reminder, are these electrons and the muons. We're only looking at these two types of leptons in this analysis. And these will provide pretty much like clean information. They're easy to identify. We also are looking for missing energy in this analysis in the final states. So this could be either in the form of neutrinos, which would escape our detector undetected, which would again show up as missing energy in the event, or missing energy could be in the form of these supersymmetric particles. So again, this chi01 tilde is the LSP, which is stable, does not interact with matter. So if it were to be produced in the detector, it would show up as missing energy. We're also looking for jets in this analysis, in specifically the form of initial state radiation. So before the protons collide at the LHC, they radiate a bunch of particles like gluons and things like that. And so we want to use this grouping of information, this jets, which would usually be just reconstructed as noise. We actually want to use this noise to our advantage in our analysis in a way that I'll explain in a slide or two. But before I talk about initial state radiation, I just briefly want to talk a little bit more about what compressed signals are. What does compression mean? So you see in this Feynman diagram up here, you have two particles coming in and colliding, or sorry, two protons coming in and colliding, which could potentially produce two supersymmetric particles, so a stop and an anti-stop, which each of them would then decay into a standard model particle, a top in this case, and the LSP. And what happens in compressed scenarios is that the mass of this parent particle, this stop, the mass of the LSP, are very, very close together, which means that there's not a lot of energy, there's not a lot of momentum going into the standard model particle and whatever it would eventually decay to. In this case, we have a top, which usually decays into a B quark and a W boson. The W boson could continue on to decay into a lepton and a neutrino. So that lepton in the final state would just not have a lot of momentum. It would be very difficult to detect in our detector. And so one way to address this issue of compressed signals is to use the ISR system to our advantage. And so what we want to do is we want to use this ISR system, this initial state radiation system, to kind of give this entire sparticle system a kick. And you can kind of think of this intuitively as if you were on a hike and you come across a rock and you're like, wow, that's a really nice rock. I wonder how much it weighs. But you're on a hike, so of course you don't have a scale. One thing you could do to get a little bit more information about this rock is you can kick it. And depending on how hard you kick it and how far the rock goes, you can get some more information about how much it weighs or what's going on inside. And that's what we're doing with this ISR system. We want it to recoil off of this particle system like you're kicking a rock, which will give us more information about this particle system it's recoiling off of. Can't use my arrows. Okay. Secondly, we want to analyze events using this recursive jigsaw reconstruction method, which was developed by Professor Rogan, and I'll give you guys a very cursory overview of how this works. So basically what happens when we're at the LHC is we have these different rest frames or these different reference frames that we can iterate through. We want to recursively iterate through each of these rest frames, each of these reference frames. And the way we get from one rest frame to another is we apply an interchangeable rule, kind of like a jigsaw piece at each step. So in this particular schematic, you can see that we start in the lab frame. We can iterate down to the center of mass frame where the protons collide. From there, we have our ISR reference frame recoiling off of our sparticle reference frame, which can then be further decomposed into our visible system, which includes leptons, and our invisible system, which includes either missing energy in the form of neutrinos or potentially supersymmetric particles. And so what's great and really useful about this method is that this gives us a whole basis of observables or basis of variables instead of just one. So we're getting a lot more information out of our event than we usually would. And if anyone's interested in the nitty-gritty of how this method works, I've linked the archive paper down here. Furthermore, we can separate our data into regions by sensitive variables. And what I mean by sensitive variables, you can see here in the middle of this slide, we have two different particular variables for this analysis. We have this mperp variable, which is going to pick up information about the mass difference. So again, how compressed this event is. You can see mass of the parent minus mass of the child will just give us delta M, change in mass. And this other sensitive variable, RISR, will actually pick up information about the ratio of the parent to child mass. And just as an example of what I mean by parent and child, I have this Feynman diagram here. And there's a lot of math that went into the derivation of these variables. But what you need to know is how differently they behave in background versus signal. And so you can see down here, I've included some plots of just that. On the x-axis for all of these plots, we have the mperp variable. On the y-axis, we have this RISR variable. And the color, or the z-axis, corresponds to how many events are in that little piece of RISR and mperp. And you can see here for background on the left-hand side of the slide, everything is very spread out. There's even this kind of sloping behavior here in the background, whereas when you move to signal, especially for compressed masked scenarios, you're getting a lot of your events concentrated in just a very small area of RISR and mperp. And that concentration becomes even more extreme the smaller mass difference you go. So we can exploit the difference in the distributions between signal and background to further separate them. And this is exactly what our sensitive or discriminating variables should be able to do in analysis. Finally, we're also looking at different kinds of categorizations in our analysis to further separate our data into search regions. So we also are looking at the categorization according to, for example, number of leptons, number of jets, soft secondary vertices, and number of V jets. And you can see the reason for this is because in each of these different Feynman diagrams of potential production of supersymmetric particles, they will, decay into different kind of final states. We want to be able to discriminate them in our analysis. And so something we have to take into account when we do searches like these is something called the fake leptonic background. And just as a reminder, the kind of leptons we're looking for in this analysis are up here. We have our electron and our muon. And what we do in this analysis is we categorize these kinds of leptons based on how good or signal-like they are. But detectors aren't perfect, and so sometimes we get imposter leptons. And just as a quick run through of the kinds of leptons we can get in this analysis, we have these good leptons, also known as prompt leptons, and these are real leptons that come from a decay immediately of a signal particle, like a lepton, or coming from a decay of a W boson. As you can see here, the good leptons are circled in green. We can also get like mediocre leptons, which are still real leptons, but they are non-prompt. So they're not coming directly from a boson or a sparticle. They're actually coming from a hadronic decay. And what happens when a hadron decays, it creates this jet, this shower of stuff, and something that could come out of that cone or that shower is a real lepton. And so that's something we want to take into account. And then finally, we have things that are just absolutely fake, not real leptons at all, completely just mismeasurements in the detector. And an example of that could be a jet, something like this, actually just punching through to that final muon chamber layer that you saw earlier in the CMS detector. And so the muon chamber lights up and says, hey, there's a muon here, but actually it wasn't a muon that caused that, it was a jet. And so that's also something we want to be aware of. And the way that the fake leptonic background is usually taken into account in analyses is with something called the fake rate method or the tight to loose method. And you saw earlier that we want to separate our data into these different regions, and it's for reasons like this, so we can kind of get a different handle on what's going on in different areas of our data. And so for the fake rate method specifically, what we want to do is we want to start with the measurement region. And this is a region that has a lot of fake leptons. We're very confident that we're not going to get a lot of real leptons here. And in this measurement region, we want to measure something called the fake rate, which is defined down here. And we want to take the number of tight leptons to the number of loose leptons. And you can think of tight and loose as just how strict you're being on the quality of your lepton. And so you can interpret the fake rate kind of as the probability that a loose lepton would accidentally pass these tight requirements. And so once we get this fake rate, we can bring it over to another region of our data called the application region, which is very similar to where we eventually want to go in our signal region, but it still has some fakes. It still has some of these fakeable objects. And generally, the way we define these fakeable objects is with a quantity called isolation. So if a lepton is less isolated, that just means there's a lot of stuff happening in a certain area around the lepton. It's more likely that it comes from this kind of hadronic decay than if it was very isolated or there wasn't a lot of activity going around in it. And so the way we're able to eventually get to the signal region is that we apply or we weight the number of fakes in the application region by this probability, by this fake rate, and then from there we can estimate how many fake leptons we should expect to see in our signal region, which is ultimately where we are looking for new physics. And so we want to get a handle on how many fakes are in there. But this method could be improved. It's not that general. It doesn't take into account something called changes in shape. And what I mean by changes in shape is the following. So earlier, you saw these two-dimensional histograms in our sensitive variables, M-perf on the x-axis, RISR on the y-axis. And these red dotted lines just represent bins or cuts in those sensitive variables. And so we can take these cuts or these bins and turn it into a one-dimensional histogram that looks something like this. And this is just a schematic that I drew up for this talk. So you can see we have normalized number of events on the x-axis. Again, both sensitive variables this time on the y-axis. But when I say shape, what I mean is literally just that, the shape of this histogram. So you can see real leptons are in black, potentially shape changes due to fake leptons are in red, and the shape is just represented by both of these dotted arrows. And you can see they're different because that's the effect that the fake leptonic background has on our data. And so I want to take into account how these fake leptons change the overall shape of our data. You can also see from this two-dimensional histogram that bins that are adjacent to each other should behave more or less similarly. We want to take into account the crosstalk between bins when we look at the shape variations due to fake leptons as well. And then finally, I mentioned previously that we do have a couple of different kinds of fake leptons, and we want to see how these different kinds of fakes affect the shape. Maybe they affect them differently. And so what we're doing in our method, it's a couple of steps. So the first step that we want to do is we want to compare shapes across different regions. And for this histogram, moving my zoom window around again. For this histogram, again, it's the same one-dimensional histogram with our sensitive variables on the x-axis. You can see what the bin number corresponds to in RISR and M-perf here on the right. We're comparing single lepton events in the lepton flavor. So we want to look at what the difference in shape is between single electron events and single muon events. And what we want to do is this first plot up here is just a direct ratio. So we take the, for example, electron histogram, and we divide that by the electron plus the muon histogram. So how does the individual histogram shape vary compared to the total consolidated histogram shape? That's what this top plot is giving you. And you can see in this first bin here that both of the values are very close to 1, indicating very good shape agreement. But as you move out to further bins, you can see the values deviate a lot more, and that indicates less shape agreement. And so this kind of gives us an intuitive, kind of quasi-qualitative insight into how much the shapes are changing. We wanted to get a more quantitative handle on how we can categorize how close shapes are in similarity. And this is where this bottom plot comes in. So what we did here is we wanted to look at the likelihood ratio of the two histograms. So what our likelihood ratio is comprised of is our null hypothesis, which is that the shapes are similar, and our alternative hypothesis, which is that the shapes are different. And so we can calculate this likelihood ratio for each of the individual bins, as you can see here. Because this is the log likelihood ratio, we can sum these up to get an overall likelihood ratio value for each of the for the electrons and the muons. And because we can get a likelihood ratio, we can take that one step further and get a p-value from that likelihood. And just as a quick reminder, a p-value tells you the probability of getting that value of your test statistic or higher in this case. And so you can see here under the null hypothesis, we get about a 40% chance of getting the likelihood ratio that we got for both electrons and muons, which is nowhere near the traditional 0.5 p-value that statisticians usually use to make certain decisions about their data. So we can confidently say that these shapes are in pretty good agreement. And once we've compared two different shapes, we can, if they are in good agreement, as you can see here, we can create a consolidated shape from them, which just means we add them together. And what we want to do with this consolidated shape, it will connect the bins together, which is like we said we wanted to do earlier. We wanted to make sure that we get that crosstalk between bins because that's how we expect they would behave. And it also will improve our statistics. And so once we have this consolidated shape, what we can do is simulate variations on top of that. So like I said, we expect the fake leptonic background to vary our shape when we look at data, and we want to be able to capture that variation. So we want to give our histogram some wiggle room. And what you can see here are two different histograms, which you can kind of interpret like a Gaussian. This black histogram, which is our central value, you can kind of think of as the mean of the Gaussian. And then you can have a 1 sigma deviation in one direction, a 1 sigma deviation in another direction, to give you that wiggle room. And so if we see anything that deviates particularly much from this, we know that it's probably not due to fake leptons. Whereas if we didn't have this uncertainty on the shape before, we wouldn't be able to make that decision. And so what we hope to achieve with this method is less of a chance of seeing false positives. So we want to more accurately predict the fake leptonic background. This method is also just a more general approach and has more information included in it. And like I said, more accurately predicting fakes will help us better see what's happening in our data, including hopefully new physics. And so just a quick recap of what we are trying to do, what our method is at the bottom of this slide too. What we want to do is first compare different shapes across histograms, use that to create a consolidated shape, which will fill in gaps. So it'll help us improve our systematics or our statistics. And then it'll also connect the wiggle of different regions or different bins. And then we do that wiggle or that simulated variation on top of the central value histogram to more accurately predict the uncertainty in the fake leptonic background. And so just to quickly wrap up, I do want to give some preliminary results for this analysis. In first, the form of event yield plots. So at the top, you can see this histogram that has the number of events on the y-axis. And on the x-axis, we have these categorizations that I was talking about earlier, where we split up the data based on the number of certain physics objects that are in that event. And so the way you interpret this plot is that this first region here, you can see you have different kinds of bins. Each of these bins is further unrolled into more physics objects throughout the rest of the histogram. So this top plot, you can see we have less compressed signals, which are these just open line histograms instead of the solid ones, which are our backgrounds. And then on the bottom, we have signals that are more compressed. And you can see even in these more compressed scenarios where we only are getting a mass difference of like 10 or 20 GeV, we're still getting some signal yield, which is good. And then on the next slide, what you'll see is this particular set of bins unrolled into our sensitive variables. And so you can see here we have our sensitive variables on the x-axis. So we have mperp and RASR, and then just further categorizations of the events based on the physics object count. And you can see that as you get higher in RASR and mperp, you have this signal event count peaking, just like we saw in those 2D histograms where for background, the events were pretty uniformly spread out throughout the entire mperp RASR space, but signal was really, really concentrated in that upper left-hand corner. That's exactly what you see in these 1D event yield plots as well. And not only do the signal event counts peak up here too, but we also see a reduction in background event counts as well, which is very, very exciting. And even though there are not a lot of, there are some bins that just don't have a lot of signal events, those aren't completely useless to us. We can actually use these finer categorizations that have not a lot of signal events to create control regions that help us better constrain our background. And then finally, just some preliminary limit plots. So the way you can interpret these is that to the left and below each of these lines, we are 95% sure that if new physics existed, we would have seen it already at these values. And so in this plot on the left, we have the mass of, in this case, the stop particle on the x-axis, the mass of the LSP on the y-axis, and here we have the mass of the stop on the x-axis, but this time we have the mass difference between the two on the y-axis. And you can see that we're able to get results. We're sensitive down to below 20 GeV, which is a very compressed scenario. And so just to close out, our group is working on a search for supersymmetry in the electroweak sector, specifically in compressed mass scenarios, what I've been doing on this analysis is attempting to create a shape-based method to more accurately model and predict the fake lepton background that we expect to see from the CMS detector. And we hope that when we include this fake leptonic background estimation method into our analysis, it'll help further refine our results and help us hopefully see something exciting. So preliminary results are looking good, and we are excited to share the rest of the analysis with you when it's ready to be done. With that, I will take any questions. Thank you.
Very good. Thank you very much, Margaret, for this very nice talk. And this estimating these backgrounds is something very important and something very complicated, as you were showing. And are there any questions for Margaret? If so, you can raise your hand. Yeah. Okay. I do have one question related to this recursive jigsaw reconstruction algorithm. Because it's the first time I see it. I'm not from the SUSY community, but it looks pretty funky, looks pretty cool. And so the first boost is along the beamline, right? But then the one where you go more to the hard scattering system, for example, or to the decay daughters of these particles, then you're not necessarily along the beamline, right? So I imagine, does that complicate, for example, the information from missing transverse energy or this kind of things? Or can you comment on this technicalities about this method? Yeah, thank you.
I can try. Like I said, this was something that Chris came up with and knows the ins and outs of very well, but I can definitely attempt to answer your question. So I believe what happens is that when you boost from one frame to another, you get like a set of angular variables, but you want to look at how the reference frames are related to each other in terms of like an angular distribution. Um, I don't think if anything, I don't think it complicates what information you get from missing transverse momentum. I think if anything, it would make it more clear. But again, like the ins and outs, I really couldn't comment on. I don't have that depth of information on me. Sorry.
No, this is very interesting, and I'll look more.
Yeah, it's really interesting,
Yeah.
but it's a little complicated. Yeah.
Are there some questions or comments? Okay, if not, let's thank again Margaret. This was a very nice, very detailed and very nice overview of your analysis efforts and the searches for SUSY with CMS. And thank you very much again, Margaret. And we'll see you next time in 2 weeks. There's one more graduate colloquium, and we'll send more information offline for that. So thank you very much again, and have a nice afternoon, everyone.
Thanks, Christian.